pergi tempat kuarantin, monitor dekat sana. Tapi dah ramai yang mati dekat rumah saya ni, kan. Dia panggil BIP ke, brought in, BID, brought in dead. Maksudnya dibawa ke hospital, dah mati dah. So, immunization pun itu adalah hak masing-masing. Tapi dekat UK, proven already, benda tu berkesan. Apa konten dia, kita tak sure lah. So, hak masing-masing, tapi selagi kalau kita tak kontrol benda ni, selagi tu betul akan ada di kalangan kita lah. Alright. So actually saya nak share gambar sebenarnya, tak jumpa gambar dia. Actually ada satu gambar dalam bidang aeronautics. Okay, dia ada satu graf yang kita panggil Mach divergence. So this is adalah Mach number. Mach number ni adalah ratio di antara speed of light dengan speed of sound. Kan? So kalau kita tengokkan drag daya seret pesawat. Pesawat ni biasanya dia akan almost constant up to certain Reynolds number, sorry, up to certain Mach number. So bila dia sampai satu Mach number yang dia panggil critical Mach number, then this drag akan mula naik. Okay, dia akan naik dan terus naik. So saya punya anggapan, okay, sebelum ni kita boleh control kita punya COVID. So kita punya numbers of cases almost kita boleh control lah. Yang awal-awal dulu kan, less than 100 dulu. Lepas tu dia dah mula naik. Kat sini ni selepas pilihan raya dekat Sabah, bukan nak blame pilihan raya tu, tapi it's proven selepas tu kes meningkat. So selepas tu kita dah ada dekat sini, sampai kat sini. So sekarang ni kes tu mungkin kita ada dekat sini, ataupun kita mungkin dah ada dekat sini. Sebab benda ni dia adalah satu masa nanti dia dilimitkan oleh tahap kesediaan, keupayaan sistem kesihatan kita lah. Kalau untuk aircraft ni, kalau dia bina wing tu kalau dibina untuk terbang untuk subsonik, bila dia dah capai supersonik mungkin dia boleh patah, kan. Wing tu boleh pecah ataupun patah in flight. Sebab bila kapal terbang tu dia terbang, dia cuba push, enjin boleh pergi laju tapi structure tak boleh nak tahan compressibility effect. So benda ni dia akan naik. Dia cuba pergi juga. Lepas tu dia akan ni lah. So dekat sini adalah, so saya rasa sini critical point kita dah melepasi. Critical point ni maksudnya critical bila kita boleh maintain kita punya number of cases tu. And then ni bila kita dah mula tak boleh nak maintain. And then kalau bila Mach number 1 dekat sini, dia dah melepasi sonic, then dia akan terus meningkat, dan dekat sini kalau structure tu tak boleh tahan, then dia akan break lah dekat sini. Tapi kalau structure tu boleh tahan, dia boleh pergi lagi. And then selepas ni kita tak tahu apa yang berlaku selepas ni. So whatever kita kena avoid daripada sampai di stage di mana sistem kesihatan kita dah in chaos situation lah kat sini, kan. Chaos situation. So sometimes this is just a logic lah, just a logic. Mungkin tak tepat kan saya punya andaian saya, tapi kalau tengokkan harian kes, we are in this stage sekarang ni. Kita punya pusat-pusat bilik-bilik ICU pun dikatakan dah sampai dah hampir penuh, kan. Pusat-pusat kuarantin pun dah 90%. So nanti yalah, hopefully dengan PKP yang akan mula lusa ni, akan meredakanlah benda-benda ni. Alright, saya ada air dengan saya ni, teh panas. You all pun kat rumah kan, kita buat santai-santai je hari ni. So sambil-sambil tu boleh kacau-kacau air, sambil-sambil makan breakfast juga. Sambil-sambil dengan lecture. Actually lecture ni macam saya cerita sebelum ni, actually sama je dengan yang apa yang ada dalam YouTube. Kalau you all miss dekat sini pun actually you still masih boleh apa ni, boleh follow up dekat ni lah, dekat YouTube. Alright, okay, untuk hari ni kita akan saya mulakan dululah kita punya kuliah kita hari ni dengan Ummul Kitab untuk yang beragama Islam, dan yang bukan beragama Islam boleh mengikut cara agama masing-masing lah. Al-Fatihah. Alright, okay, untuk hari ni kita mulakan dengan kita review semula pada part boundary condition ni. Untuk heat transfer, untuk heat transfer problem, at least kita ada 3 jenis boundary condition kan. Okay, yang pertama adalah dikenali sebagai condition yang kita tahu suhu pada permukaan surface kita punya komponen tu, ataupun known boundary conditions ataupun specified boundary condition. So kalau saya dapat ingatkan semula, untuk kita selesaikan heat transfer, so the system of linear equation yang kita akan solve adalah dalam format KT equal to R. So K adalah kita punya saya lupa dah nama dia apa. Nama dia elemen conductivity elemen conductivity matrix, betul. K adalah elemen conductivity matrix. T which is our temperature, which is we would like to predict it. So dalam numerical ni biasanya kita panggil predict lah. Predict kita instead of kita measure ni dia macam lebih tepat sikit kan. Measure biasanya kita guna untuk eksperimen, measure. Predict, so kita pakai untuk numerical, mostly kita pakai predict to predict temperature distribution. So NR adalah heat rates vectors. So R adalah hanya akan ada value sekiranya adanya internal heat generation dalam kita punya sistem. Kalau tak ada, R will be always equal to 0. Cuma untuk the temperature boundary conditions in the type of specified temperature on any surfaces of our component, then in order to apply the boundary condition, kita kena assemblekan dulu ke semua kita punya KT dengan R, barulah boleh kita applykan boundary condition. Kalau dalam kita punya structural problem dulu, kita boleh apply boundary condition pada local stage. Maksudnya pada kita solve element by element tu, kita dah boleh apply boundary condition kan. Tapi Untuk heat transfer ni kita tak boleh buat macam gitu. So we have to apply it after we assemble a complete system of a linear equation, then baru kita apply itu punya boundary condition. So dia punya approach dia untuk specified heat, specified temperature on any surface, which is we can measure it. Then kita akan eliminate the rows and column on that particular surface. So sekiranya berlaku temperature tu, kita tahu pada surface nodes pertama, then kita eliminate the whole rows dengan column yang pertama. Tapi we have to modify kita punya system of linear equation by adding this term dia K multiplied by theta, which is theta is the temperature on the surface itself. Bukan kita ambil theta T dekat sini. That's mean theta on which is the temperature on the surface akan didarab dengan the whole element of K yang kita eliminate tadi. So we bring all the K, the column vector K yang kita eliminate to the right hand side equation, and then we multiply by the temperature T. So all of them. So that's the first one. So kita ada example nanti. So yang keduanya adalah the convection. So untuk convection boundary condition, that means there is a heat transfer process occurs across this plane wall. So to further increase the heat transfer process on the right wall, so dekat bahagian sini ni, kita nak improvekan dia punya heat transfer. Kalau kita tak ada convection ni, heat transfer daripada surface ni ke udara ni mungkin dia still berlaku, tapi pada kadar yang slow. Okay, bila kita blow air pada temperature yang tertentu, pada convection coefficient yang tertentu, then dia akan increasekan kadar pelepasan haba daripada surface ni ke udara lah. So that's why kita ada konsep fan, air cooler apa semua tu kan. So in this kind of problem, so we do not need to eliminate because kita tak tahu ni berapa suhu dekat sini ni, sebab suhu pada surface dengan suhu ambient tak sama. So kita tak tahu temperature dekat sini pun kita still tak tahu actually. So in that case kita tak boleh eliminate the row and column. So what we have to do is we still have to modify. Okay, actually kita punya, kalau kita ingat lagi, kita punya equation KT equal to R. So untuk this case we have to add the right hand side by H multiplied by T. Tapi yang ni adalah hanya apply kepada the surface where it exposed to the convections. On the left hand side pun we have to add the K here by H. And then similarly, yang ni hanya apply kepada the matrix element which is representing the last equation lah, ataupun representing this nodes on the surface of the plane wall. Dia bukan tambah semua ni, bukan dia tambah semua, tapi hanya apply kepada the surface that exposed to D. So kalau saya boleh tambah kat sini ni, only apply to this one as well. Only apply to surface exposed to convection. Tapi kalau nak senang ingat dia, roughly macam gini lah. K plus H, kita ada T plus R plus H multiplied by T. So H adalah H convection, T adalah T the convection. And then it just apply only to the nodes that are exposed to the nodes which is representing the surface that are exposed to the convection. Let's say kalau saya ada surface dekat sini, and then surface ni pun ada convection both sides, sebab kita let's say kita ada internal energy, internal heat generation kan. So R kita ada value. So dekat sini pun kita ada convection, tapi dia punya temperature dengan H dia mungkin lain. So what we have to do adalah we just apply to the nodes number 1, which is yang this one lah, K plus H, and then this one plus dengan T multiplied by H untuk yang biru ni. So that's it. Yang lain-lain jangan kacau. Okay, next is the heat flux. So in some cases, we would like to stop the heat transfer from one region to another, which is this is the case where mathematically we can represent it by the heat flux boundary conditions with Q, heat flux equal to 0. Okay, itu kalau kita nak tepatkan dia, kita nak stopkan the heat transfer ataupun kita nak slow downkan dia. And then if sekiranya we are to solve this kind of problem, then again we have to modify our system of linear equation, KT equal to R. So kita still solve equation yang sama je, KT equal to R. But in this case, we have to modify the right-hand side equation by including the contribution from the heat flux, heat flux across the system, across the surface actually. So in this example dalam slide ni, which is we have heat flux that occurs on the left surface, which is kalau dalam case ni this is our origin, x equal to 0. So pada point 1 lah kat sini, and note number 1. So in this case we just need to modify the right hand side equation by including the heat flux to the nodes or to the equation number 1. So the whole rows ni adalah merujuk kepada equation pertama untuk nodes number 1. Yang bawah ni merujukkan, actually this is all equation ni, equation kan, kalau kamu multiply K T1, K12, T2, dia akan menjadikan satu persamaan matematik kan. So equation 1 adalah untuk nodes nombor 1 lah in this case. Kalau kamu ada 1000 nodes, so ada 1000 lah equation. So since the heat flux occur on the surface number 1, then we have to modify the right hand side equation by including the heat flux to the equation number 1, which is to represent the heat flux add nodes number 1 in this kind of problem. Kalau berlaku heat flux dekat sini juga, kan? So kat sini masuk, dia keluar dekat sebelah apa ni? Sebelah surface bahagian kanan. So what we have to do, then we modify this equation. Instead of 0, initially 0 sebab tak ada berlaku kan sebelum ni. So bila I add, let's say I simulate the heat transfer juga berlaku pada sebelah kanan, then we have to modify. Kita removekan dulu. So dekat to the last equation here, then we have to include positive. So you have to be careful with the positive and negative. So dah ada note dekat bawah ni. It says that Q naught is input as a positive value if heat flows out. Kalau heat mengalir keluar daripada bodies ataupun daripada sistem kita ni, so we will have a positive value of heat flux. Kalau heat flux is moving from ambient ataupun from outside of the body into this body, so the value will be equal. We represent it by the negative heat flux. So this is just as what we call it revision lah, what we have done in the previous meeting. But previous meeting agak tergesa-gesa kan, so kita slow down sikit hari ni. So now let's look at these examples. So kita rehat 2 minit, minum air sikit. Lagi satu guys, saya tak pandai nak buat humor ni, tak pandai nak melawak. So kalau tak pagi-pagi ni kena tahan sikit lah. Hopefully semua okey lah. Sebab kadang-kadang sense of humor ni penting juga untuk menceriakan kan, nak stimulate kita punya otak kan. Kadang dia dah slow, bila kita tergelak ni dia ceria semula kan. Saya kadang yalah, lagi kelas online ni tak tahu nak buat lawak apa. Kalau kamu nak lawak, nak stimulate your mind ke, your brain ke, buka lah YouTube apa-apa sekejap kan. Sebab kadang melawak ni very good. Kadang-kadang kita tak sedar apa yang kita buat lawak dia kan. Kadang-kadang dia tersentuh sensitivity. Dia setengah orang dia naturally pandai buat lawak. Okay, Okay, in this example, so kalau kita baca lah, saya baca dan saya try explain lah dekat sini. We have a composite wall. Composite wall ni that mean wall of different material combines maybe layer by layer to make one new wall yang baru kan. So we have a composite wall consists of 3 layers of materials. So kita ada material 1, material 2, material 3 lah. So yang ni K1 assuming kita ada material 1, K2 material jenis yang kedua, K3 material jenis yang ketiga. So dia tak specify exactly lah what type of material kat sini. So the ambient temperature is T0. So ambient temperature is T0. Is it correct dekat sini? So tapi dalam gambar ni ditunjuk T0 ni pada surface kan. So assume lah in this case sebenarnya tak semestinya sama. Tak semestinya sama. Tapi in this case kita just assume that T0 ni adalah T on the surface juga untuk yang sebelah kanan ni. So convections heat transfer take place on the left surface of the wall. So pada left surface berlakunya heat convection, which is given the heat convections dia adalah 800 dengan H 25 watt per meter per area per temperature per degree Celsius. So problem here adalah model the composite wall using 3 heat transfer elements and determine the temperature distributions in the wall. Alright, apa yang kita perlu lakukan kat sini adalah, apa yang kita diminta untuk dilakukan kat sini adalah untuk dapatkan temperature distribution across this wall. So ini kita punya wall, ada 3 jenis material. So untuk this kind of problem, then untuk kita punya kursus ni, to simplify this problem, then dia mentions explicitly dengan nyata kan, pakai 3 heat transfer element saja. So in this case, apa yang kita boleh buat adalah kita bahagikan ataupun kita discretize ataupun kita meshkan kita punya finite element model ni dengan 3 elemen which is mengikut dia punya material. So dia akan jadi macam gini. Elemen pertama size dia tak sama dengan elemen 2 dengan elemen 3 kan. So kita bahagikan elemen ni mengikut material. So supaya kalau saya ambil equal spacing. So equal spacing dia mungkin jadi macam gini. So agak susah sikit kita nak solvekan dia. Sebab dekat sini kita boleh solve. Kita tahu satu material, tapi kat sini kita ada 2 materials in one element. Kan? Kat sini, kat sini. Kat sini pun sama. Satu material lain, satu material lain. So it will be a bit difficult. Dia boleh solve, tapi a bit difficult lah. So to reduce the complexity, so we suggest discretize your element according to the material of your composite wall. Kalau ada satu material je, kalau satu material je, this is your block. Okay, this is your block. Ada satu je material, K1 je. So macam mana? Nak bagikan dia kepada satu je. So biasanya kan ni kalau dia minta bagikan kepada 3 juga, so bagikan kepada 3 of equal spacing lah maksud dia. Biasanya kita akan mention pakai equal spacing ke ataupun K1 kita dah bagi berapa size dia. Tapi as I mentioned, the decisions how are you going to discretize your model is actually the engineer will decide, will instruct the computer how many elements you want to have. So computer can generate according to the mathematical model yang software engineer develop lah. So dia ada software engineer yang develop finite element itself. Satu lagi kita panggil engineer which is using that software. So kalau saya pakai software, saya just bagi tahu the software how many elements I want to have for this structure. Let's say saya letak 10 elemen. So dengan menggunakan algorithm yang software engineer tu develop, actually dia ada mathematical model dia. Mungkin ada beberapa jenis mathematical model. So software engineer pick up one model untuk gunakan dalam software development. So based on based on that mathematical model itulah software tu akan generate based on input yang kita bagi, kan. Actually itu yang sepatut kamu faham dalam finite element ni, not only to solve these particular things, how the software works, Alright, now we know that we have 3 type of materials to make up of one composite walls. Then we discretize our wall into 3 elements as recommended by this problem. Then we discretize it, our structures, our wall here, according to its respective materials types. Okay. And then we label it as usual. Sebagai contoh kat sini kita dah ada. Kita labelkan T1 for the nodes numbering. We have element numbering, and then you can write kau nak tulis lah if you have time. Sebab kita pun memang nak solve temperature, so we should know that at nodes number 1 we will solve the temperature there. We will solve temperature T2, T3 and T4. So you can write as well on the right nodes we have T4, which is known already, given by 20 degrees Celsius, and then we know that on the left hand side we have this heat convections process. So this is nak tengok semula. So for this kind of problem yang kita ada ni, example 6.1, if we solve using any finite element software, tapi kita discretizekan model tu, kita punya wall tu dengan menggunakan finite elements mesh ataupun discretization yang sedikit berbeza lah. Macam yang kita buat kat sini, kita macam 1D kan. 1D problem. So actually if we solve our problem in 2D pun, okay, we will get something like this. So this is adalah results for the same problem. So the result for the same problem where we have a convection 800 degrees Celsius, and then we have 25 watt per area degrees Celsius. Dekat sini on the surface ni we have 20 degrees Celsius. So when we solve this in 2D using Nastran finite element software, so we will get a distribution which looks something like this. So on the very left surface, temperature adalah 305.8. So on the second node, we have 120. Third node, 54.6. And then on the surface here, we have 20. So let's we compare dengan 1D solution. 1D solution, which is the solution that we are going to use in our ni lah, in our course. Alright. So now we know that we have to solve our element conductivity matrix. We have to solve the heat rate vector element by element first, and then we have to combine it as usual. So we write the element heat conductivity matrix for each materials or for each element. So apa yang kita ada, kalau kita ingat hari tu kita punya K kita punya K which is KE given by K over L, and then kita ada square matrix of 1, -1, -1 and 1. Tapi K ni adalah bukan K ni. K ni adalah elemen conductivity coefficient of the material itself, which is given in the problems lah. Sebab material ni biasanya dia ada material properties. Kita nak guna material apa, biasanya kita boleh minta ataupun kalau kita tahu exactly what material that we are going to use, then we can search for all this kind of information. Kamu boleh dapat stress dia, kamu boleh dapat material, the thermal properties of that material, macam gini lah. So we have K1, K2, K3 which is given by 20, 30 and 50 watt per meter per degree Celsius. Then kita gantikan lah kat sini, which is very straightforward punya proses. So K1, K2 and K3, then you assemble similar to 1D bar problem sebelum ni. So we done with the K, very straightforward. So saya tak nak go very detail lah sebab kita dah pernah buat banyak kali. Cuma you have to be careful lah, dekat depan ni kita ada constants. So jangan tertinggal. Biasanya student kadang dia tertinggal je ni. So if you just carry whatever you have in this bracket, you forgot to multiply by 66.7, nilai dia is very very far. Kan 1 dengan 67 ni jauh beza dia. Kalau you can imagine 1 degree Celsius dengan 66, oh jauh beza. So now okay, dalam kita punya problem tadi dia tak ada mention pasal heat, internal heat kan. So you can imagine dekat sini when there is no information about internal heat generation, so R will be equal to 0 everywhere. So in this case, the only thing that you have is your K matrix, your T vector and R vector. R will be all equal to 0. Sekejap. Hello, sorry. Saya pakai earphone tadi, tapi terdengar macam bunyi orang menangis tau. Itu yang berhenti sekejap. Intai-intai tengok anak dah menangis kat luar bilik. Sorry, okay, ada gangguan sikit. Alright, Actually, kita punya apa ni, teaching session di semester much more smoother daripada semester yang lepas. Semester yang sebelum ni which is a bit more chaos juga sebab first time kita buat online teaching. Dan masa tu first implementation tu masa mula-mula PKP dulu juga. So saya ada baby kecil masa tu umur setahun, so kadang tengah ngajar tengah dukung baby lah depan-depan apa ni depan-depan skrin ni. So this time okay sikit lah. So alright, now we will come back to our discussion, which is we since there is no internal heat generation mentions or occurs in our systems, so we can expect that R vector here will be 0 everywhere. But you have to remember we still have two boundary conditions, which is the specified temperature on the right hand side, and we have the convections occur on the left hand side of our system, which is require us to modify the system of linear equation to include the both effects. Tapi for the learning process ni, you include it one by one. Okay, step by step. Jangan buat lump sum macam gini. Macam gini dia lump sum ni. If you look at step number 6 here, it's a lump sum which is you include everything. So it's hard for you to trace apa yang berlaku sebenarnya ni dekat sini ni. So for the learning process, I not recommend this approach. Actually, what you have to do, which is to detail it. So if we look closely to our system of linear equation, so I have so saya ambil semula yang ni. So I have 66.7. So I have 1, -1, 0, 0, -1, 4, -3, 0, and then 0, -3, 8, -5. Then I have 0, 0, -5, and 5. So this is my K matrix. So jangan tertinggal yang ni. Then I have T. So this is my T1, T2, T3, and T4. And all of these will be equal to so kita jangan cakap jangan gelojoh, we solve part by part. So this is our R. So my R, which is all of them equal to 0. So this is my R vector. So this is my K matrix, and then this is my T vector. So so now we know that we have saya rendahkan sikit. So in our problem we have, so this is the structure. So we have the T. So kita bagikan dia kepada 3 element. So when 3 elements, saya ada node 1, 2, 1, 2, 3, 4. So elemen 1, elemen 2, elemen 3. Ada 3 elemen. So saya besarkan sikit dia, so kita akan dapat macam gini. So I know already which is T4 given by this 20 degrees Celsius. Then I know as well the H and T here, which is 800 and also 25 watt per area per degree Celsius, which is occur on the left hand side of this surface on nodes number 1. So kita nak start dengan mana dulu? Okay, we can start with the known boundary conditions, which is yang ni kita tahu, which is equal to 20. Then we eliminate, so we eliminate this and this. And then when we eliminate the row and column, then we have to add it to the right hand side there. Nak add dengan apa? So bila you bring this to the right, jangan lupa bawa ini sekali. So you will have 66.7 ataupun nak buat macam gini pun boleh. Cuma jangan lupa je bila nak solvekan dia nanti, jangan lupa darabkan yang ini. 1, -1, 0 and 0. And this will be multiplied by the temperature 20 degree Celsius. So now we done. This is a contribution from the from this specified boundary conditions. And then all right, and then we knows that there is heat convection. Sorry, betul. Saya tersalah ni. Sebab kita potong yang ni pun should be saya tersalah. Thank you yang remindkan saya. So kat sini will be 1, -1, 0 and 0. So sebab dia berlaku pada node nombor 4, so kita eliminatekan row and column nombor 4. So dekat sini it will have 0, 0, -5 and 5. Okay, terima kasih. And then we have the contribution from this convection. So kita tambahkan dia lagi. Tambah ke tolak kalau ada convection? Cuba tengok semula. Okay, untuk specified boundary condition, ini kita kena ingat lah. We have to deduct by this values. Tapi untuk untuk boundary conditions, convection boundary condition, we add it. So mana kita tadi? Okay, when we are here, then we have untuk yang ini instead of plus, we have to minus it. So this is contribution from the specified boundary condition, and then dekat sini, then what we have to do is we add H and T dekat sini kan. Dekat sini, since the convections occurs on the first node, so we modify this, then add it by 25. So H ini adalah T. So this value here multiply by this, then plus by H. So bukan 1 plus H dulu baru darab dengan ni. So we have multiply this value in the bracket here must be multiplied by 66.7 plus H. So you will have 66.7 plus 25 to replace these numbers there. So saya buat macam gini lah, to replace okay, to replace this part here, this element, and then on the right hand side here, then we have to include 800 multiplied by 25. So yang lain-lain sebab tak ada berlaku convection kat sini, tak ada berlaku convection, tak ada berlaku, then we just fill this column vector by 0. So so if we refer back to this slide, to the slide. Okay, saya cuba tunjukkan ke semua sekali. Hopefully you can see all of them. So we have here sekejap So on the right hand side here, we have 25 multiplied by 800. Kalau tengok kat sini, yang ni adalah kosong. This will be 0, will be 0. So you will have a value here and here. And then, so for the first rows, kita hanya ada 800 multiplied by 25. So kita ada yang ni. 0 plus 0, we have this. So yang ni, kalau kita tengok, so we have 0. Yang ni, minus 66, 520. Kita ada 5, 66 and 20, which is represent this this portion. And then we have another 0 there. So yang dekat bawah, yang ni betul ke dekat bawah ni? Okay, yang ni dia ada value, tapi kita eliminate the whole thing. So actually ada value ni dekat sini, which is 5 multiplied by 20 negative value dekat sini. Tapi kita tak pakai lah sebab kita dah eliminate kan dia. And then can we check this one? So yang ni dah boleh faham kan macam mana dapat dia. Actually a contribution from the R, kita ada contribution from the T naught tadi, and then contribution from the convection. So kita ada 3 components. Okay, cuba on this in our matrix dekat sini ni. Okay. Where is this value came from? 1.375. Can someone verify this? Daripada mana datang dia? So we have 825 watt per meter square per degree Celsius. Okay, kalau kita tengok body condition yang heat flux punya body condition, so very straightforward, kita just add the K elements dalam kita punya element conductivity matrix by H. Sorry, dekat sini kan kita just tambah dia dengan H. Tapi kenapa kita dapat dekat bawah tadi 1.375? Where that number came from? Can someone help me here? Sambil-sambil kita minum teh ataupun kopi. Mana datang dia? Tak ada ni information ni 1.375 ni. Anywhere. Tak ada ni. Kan? Mana datang eh? Sebab tu you have to dalam apa ni, dalam lecture note, dalam textbook sometime dia punya shortcut dia tu dia jump very big step. So kalau you all tak teliti, you may lost lah. Actually this 1.375 ni actually came from, asalnya kita ada satu je, sorry. So we have something macam ni, kita ada satu je kan, let's say saya just ambil value this value there, and then kita nak tambahkan dia dengan 25. So what happened here was dia dividekan this dengan 66.7 supaya this number kita boleh directly add inside this, then bring the constant outside. Kan? So if you take 25 divided by 66.7, berapa you all dapat? 25 divided by 66.7, ni value dia adalah 0.375, betul, which is equal to 0.3748 lah, kita 3.75. So in that case, sebab dia nak maintain benda ni dekat luar ni, so dia akan tambahkan dengan 0.375. So dapatlah macam gini. Actually this apa yang kita ada dekat sini ni, ni so apa yang kita ada dekat sini actually is the same as 66.7 plus 25 as we did here ni. So itu je. Just maybe a bit confusing lah kalau you all baca this slide. Saya mula-mula ngajar dulu pun sebab this slide kita just receive from senior staff yang sebelum-sebelum dia ngajar. So apa benda ni kan. So my approach very simple je. Kalau kita jumpa benda-benda susah, we go to the most very basic kan. Solve it step by step. Step by step. So bila kita solve step by step, so we will get something like this. Kita nampak it's clearly macam mana K kita diubah, the right hand side equation kita apa components yang kita perlu modify ataupun kita perlu tambah kepada right hand side equation kita. And then if we solve everything dekat sini, finally kita akan dapat sama juga dengan apa yang ada dalam slide ni. Okay, kita akan dapat benda yang sama dalam slide ni. So when you reach this stage, okay, you only have 3 unknowns, and then this is very straightforward for you to solve by using calculator lah. So in this stage, you are allowed to use a calculator lah to obtain the unknowns in your matrix or system of linear equation. So bila tekan calculator, then you will get this temperature distribution ataupun temperature at each nodal point. Tapi kalau boleh, meskipun soalan tu tak minta kamu plot the graph tu kan, kamu plot lah sikit, tak ambil masa lebih 2 minit pun, which is engineer dia bukan hanya generate numbers, okay, tapi dia also generate understanding. Kalau just baca numbers macam gini, 4 number gini will be easy for you to understand. Tapi when you have more numbers, kamu tak boleh nak faham dah number tu. Apa yang boleh kamu faham adalah figures. So numbers when it translate into figures, so let's say kamu nak buat macam gini boleh, tak nak tulis, ni tulis notes numbers. Let's say notes number 1, notes number 2, notes number 3, notes number 4. Kan dia distance dia tak sama kan. So dekat sini you have temperature. So degree Celsius. So notes number 1 is at 300 roughly, just sketch here, not need to write it into scale. Let's say kamu ada situ adalah, let's say ni adalah 300, this is 200, so this is your 100, 0. So now it will be easy for you to draw. So this is your first point there. Second point, you have 100 and a bit, which is there. If you project it there, ada dekat sini. And then you have next is 57, which is roughly halfway. And then you have 20. So draw je lah straight line. Kan, it's much more clearer to see. Okay, this is how the temperature distribution looks like. So it don't take you more than 2 minutes lah untuk this. I think if you go to work, you just not generating the numbers. No one interested in the numbers because kita tak boleh nak digest. Our brain cannot digest the numbers. Rather, we would like to see. Macam you all buat project lah. Finally, you have to show the contour. Kan, contour tu adalah number tu sebalik contour yang color-color tu. Tapi if the computer just give you numbers, kamu tak boleh nak analyze which one having higher displacement, which one is having, or which part of your structure having higher stress area. Susah nak faham. So you have to change a bit of your mind. Don't stop until number. Try to plot it. Try to plot. Every time you got the numbers, try to visualize what the numbers means actually. Okay, that will give you sedikit anjakan pemikiran lah dekat sini. Because we are here in the university, it's not like in the school. Sekolah tu dia nak tahu proses, kira. But we in the university, we need to have the mind that which is kita nak educate orang lain dah pula ni kan. When we solve something, when we solve one problem, it's not only for us. We would like to tell others, okay, ni lah result dia, macam gini result dia. Kita nak, we not only need to explain to our boss. If you are nak buat produk kan, then you have to convince the buyer as well, and your, dia panggil apa your partners lah kan, partners in business kan. So dia orang tak nak tengok numbers. Dia orang biasanya bos ni dia nak tengok pertama sekali nak tengok boleh ke tak boleh. Tu je. Boleh ke tak boleh? Kalau tak boleh, okay, cari cara lain ataupun jangan proceed. Kalau boleh, okay, apa result dia? Dia tak nak tengok ni number yang banyak-banyak ni pening kepala kan. So move a bit ahead daripada orang lain. Kalau orang lain just generating numbers, you should be able to visualize it. Yang ni pun tak susah je. In fact, untuk topik-topik yang sebelum ni pun sama. Try to plot it. Try to plot. So if you go outside later pun, kalau you have to lead a team, kan, you engineer nanti keluar. So nanti ada staff under your supervision. So dia duk kira je keluar number kan. So terus dia plot sikit. Baru kita nampak, oh macam ni distribution dia, linear ke tak linear kan. What is the equation? Actually we can generate equation so that we can interpolate what is happening in between ni, dekat sini kan. So that kalau dalam apa ni this in this course we can use TX sebagai contoh, N1 T1 Allahu Akbar plus N2 T2 in order to obtain, let's say I would like to determine the temperature there. But through the graph you still can get it. Tapi mungkin dia tak accurate. Kan? Tapi bila kira ni much more accurate. So if you can generate the equation for this graph, dalam Excel boleh generate equation. So you plug in the numbers dekat sini yang you nak, masukkan dalam equation dia, dah dapat temperature dekat sini. So that is another way of doing it. Alright. Okay, that is one examples lah. One examples on this heat transfers to the plane wall. So now untuk yang ni saya rasa saya tak nak explain in detail. The process is the same. Cuma saya nak tanya, what will be happen if as you can see the convections semua dalam arah ke atas kan. So what will be happen if the convections on one side dekat sini ni instead of dia ke atas, dia ke bawah. What will be happen to the value lah, at least the temperature and H on the left hand side of our wall. But kita kena substitute dia ni. Kita kena substitute dalam kita punya K matrix dan juga right hand side equation kan. So what will be happen? Betul, Aiman cakap still the same. Betul lah tu. You can imagine macam gini lah, kipas kan. Kamu duduk depan kipas ataupun kipas blow daripada belakang kamu rasa sama je dia punya the speed of the fan tu. Speed of the fan, at least the temperature dengan convection dia tu sama je. Dia tak akan jadi negatif pun. But dia through this surface kan. Kalau dia blow macam gini mungkin kan blow macam gini, yang kat sini mungkin ada kesan. Kalau dia blow macam gini, yang ni kuat lah rasa, tapi kat sini temperature dia dah lain kan. Tapi in our case this convection process occurs parallel to the surface, so dia tak ada effect apa pun. So dia akan maintain H and T dengan value yang sama, dia tak akan jadi negatif pun. So substitutekan dia dekat in your okay, cuma dekat sini as you can see kita ada internal heat generation. Cuba tengok soalannya semula. Okay, heat is generated in a large plate. Okay, heat is generated in a large plate, which is ada satu single piece plate of the same materials. So ini adalah dia punya heat conductivity at rate 4000 watt per volume. So we can imagine kita punya blocks ni is a macam brick ke apa kan, ataupun kita ada macam bar ke, ataupun thick plates ke. Then untuk 1 meter cube size, okay, let's say 1 meter cube size, dia akan generate about this much of heats internally. So kita boleh imagine macam kita ada internal combustion engine ke macam gitu kan, something like that lah. The plate is 25 meter thick, which is quite thick, and the outside surface of the plate are exposed to ambient air at 30 degrees Celsius with a convection heat transfer coefficient 20 watt per meter square per degree Celsius. Tapi ini dia minta kita guna 4 heat transfer element. So when there is explicitly mentioned the heat generated in the system, then our R value, the element heat rate vector, will have some values, which is as shown here. Yang K dah boleh faham kan? Yang K is straightforward. K. Untuk yang R vector, so everywhere is generating the same amount of heat. So the way we solve it, so kita akan substitute the value of the heat generation to all elements lah. Kita ada 4 elements, so kita generate it with the same amount of heat, internal heat generation. So kita akan dapat macam gini, R1, R2, 3 and 4. Then we assemble it. So when you assemble it, so you akan dapat the global heat rate vector as shown here. So ini pun kita assemble macam biasa lah. Kalau ingat lagi kita ada note kan, kita boleh tabelkan dia sebagai note 1, 2, 2, 3, 3, 4, 4, 5. So yang overlap ni kita tambahkan dia je. So 1 to 5 plus 1 to 5 you have 250. 1 to 5, 1 to 5 you have another 250. 1 to 5 to 5 you have 250. Satu dia single dia 1 to 5. Yang 5 pun dia ada single values dia, which is 1 to 5. So alright, since we have two convections processes occur on both sides of our plane wall, so we modify the K on both sides, and then the apa tu kita punya right hand side equation also we just modify to the first equation and the last equation sahaja. This is which is very straightforward lah. Cuma untuk this problem, kamu tak boleh nak solvekan dia apa ni pakai calculator lah, sebab you have 5 unknown dekat sini. So tapi biasanya as I selalu ingatkan, untuk this course sajalah, untuk kita punya course saja, we limit the number of unknowns maximum 3, which is it will allow you to solve the problem using your calculator. If we have more than 4, then tak boleh nak solve lah pakai calculator. Otherwise you have to use the manual calculation to solve the Gaussian elimination, kan? Tapi yang tu kita dah go through topic plane trusses, which is you have to manually calculate the Gaussian elimination. So actually this course ni I think after I join teaching this course, I have been teaching sebab bila first time tu kita tak nak ada banyak perubahan kan, kita tak tahu apa nak ubah. So while we go through, we improve how we test the student lah, test the understanding, comprehension of the student toward this course. So kalau tengok soalan yang zaman-zaman dulu punya, kalau kamu collect soalan zaman-zaman dulu, ada yang lebih kurang, which is soalan, the problem itself dia tak ada so much way to apa ni, we play around lah kan. So some other problem we can play around with it. So the question yang kalau kamu ada collection of the past semester punya question, I think 5 years and above lah. Soalan dia agak-agak beza dengan yang sekarang ni. The way we I think since 4 or 5 years back lah, we start to change the way we tell the student. Macam yang test 1, we test you but we guide you. Okay, macam dulu dia test tapi dia tak guide kan, sama je. But we guide you supaya even though we test you, but we still guide you so that you do not lose. But this is a learning process kan, the learning process. What for we teach you if we can't guide you for the first place kan. Macam budak-budak nak berjalan kan, someone have to show macam mana nak jalan, pimpin dulu. Then when you have you know how to walk, then you walk by yourself lah, kan. So the same process. So we improve it. Then the same in the test too, we still guide you, but in the final exam, and then in terms of mathematics as well, you have done mathematics so much sebelum ni. Daripada sekolah, masuk tadika je dah kira 1 campur 1 kan. Budak-budak sekarang ni lagi lah, dia ada ujian, tadika pun dah ada ujian sebelum ni. I think few years back lah, 4 tahun lepas ke apa kan. Sorry, betul lepas anak saya yang first dah tingkatan 1, masa dia tadika dulu pun dah ada ujian. Nak masuk darjah 1 ada ujian. Siapa dapat skor bagus boleh duduk kelas depan. Tapi sekarang ni dah tak ada. Which is for me, okay, that's a good. Okay, sometimes it's good to put together good student. Okay. Tapi dia ada pro and cons masing-masing. Actually kita dah habis topik ni, and then next topic tu kita akan discuss dalam next lecture. I just ni lah, just sembang-sembang sikit. Actually I'm not very well actually today, nak pergi jumpa doktor juga ni sekejap lagi ni. Tapi kita sembang-sembang dulu. Sambil-sambil tu pun saya boleh sharekan apa ni, nanti kalau you have any question just tanya je dekat sini. Actually saya kadang-kadang agak tak setuju yang a good student just among good student, because we shouldn't build our country in that way. Actually what should be happen adalah if we have a group of good students, so these good students should actually be put together with yang agak slow. Kadang-kadang dia agak slow tu dia mula-mula je dia slow sebab dia tak faham. So when this group of student yang tak faham ni dia dah boleh faham dengan bantuan kawan-kawan dia kan, kawan-kawan yang cepat fast learner ni, okay, dia bantu. So then we will have more people with good knowledge. kalau kita just separate it, so kita hanya ada semua group je lah yang good, yang lain yang kurang, kan? So that's why in apa ni, in apa ni, projek ke apa, saya just bagi je nama. So you have to manage. Okay, mungkin ada yang bagus dalam group kamu tu. So yang bagus ni, okay, dia ada bagus dalam satu benda, dia memang bagus. Tapi bukan semua benda dia bagus pun sebenarnya. I have seen this kind of people, even though dia nampak bagus, dia bagus, tapi bukan semua benda dia bagus. Tapi um, uh, some people ni, which is kita katakan dia on the paper lah, dia macam tak bagus kan. Tapi when it's come to hands on, dia lagi bagus daripada yang on the paper yang bagus tadi tu, kan. So actually you have to work together. Setiap orang dia ada apa ni, kebolehan masing-masing. And then if our country want to go far further kan. So yeah, life is not a race. We have to work together. Kalau kita nak race, dia macam gini lah, kita kerja seorang-seorang, kerja in team. Kan? Kerja seorang-seorang, kamu boleh buat lah apa yang kamu nak buat, whatever you want to do. Tapi you will progress very very slow. Tapi yang work in team ni, dia bekerjasama, seorang ni buat sikit, orang ni buat sikit, sana buat sikit. So dia boleh progress very very fast. Meskipun yang dia buat mula-mula tu benda yang biasa-biasa. Then bila dia dah sama-sama develop the understanding, then you can go quicker and far more than yang kerja seorang-seorang tadi tu. Alright, dah hadir, dah keluar tu, okey lah, you all nak keluar, dah bosan dengan saya duduk sembang-sembang pun boleh keluar. So kita tutup dululah dengan tasbih kifarah dan suratul as. Alright, thank you very much for joining me in this lecture today. Assalamualaikum and take care guys.